This conference will now be recorded.
So today, guys, we are going to deep dive in the SVM. We started a little bit with it last time, and I hope that, well, not necessarily understood everything about it, but you are more or less okay with what we did last time. Today, we are going to go deeper in this model. So yeah, this is it. So you have seen that it is quite related to logistic regression. It shares many similarities between logistic regression and the SVMs, the support vector machines. Like logistic regression, the SVM try to separate, at least the first version, the linear SVM, try to find the optimal hyperplane. But it is defined by maximizing the margin in here. So originally it was dealing with linearly separable problems like this one. So it finds a line or a hyperplane in high dimensional space that maximize this margin. We want it to be at its maximum. So here it will be something like that. We can have like a lot of lines that separate like these two data points, many. But by instinct, just by intuition, you can easily tell that this is probably the best one. Why? Because the margin is quite large here. We have higher confidence. Here we are not sure if we are doing, for example, a good job or not. It's because we are close to here. So if a point in here or in here is classified as a triangle, we might be wrong because it's much closer to here and the hyperplane is in here. So here the confidence values is low in this region. Here it's really a bad line. It's classifying well these triangles, but not these circles. Here it's classifying them well, but again, you can see that the distance here is very small. So the confidence margin, if I can call it that way, is small. Here we can see that the distance is very large between the two. And this is a good intuition to start with building this kind of models. So this is what the SVM way of doing things, or how to find the hyperplane, is formulated. We want the hyperplane or the line that maximizes the margin, this margin. Here it will be this one. So the margin is this. And these points are called the support vectors, those that are connected to the margin borders. Here we have the margin borders, and we call these points the support vectors. They are the points that define the margin. So you just choose, yeah.
Sorry, the quick question. So when you say you want to maximize the margin, is that because you want to be able to discriminate quite easily or have a high discriminatory power between those two data sets or those two data points?
Exactly. We want the higher confidence in discrimination, in making the difference. And the hyperplane that maximizes this margin will give us like more assurance in the way it is doing things. When, for example, you are going to work and you have more time allocated to you, which is like the margin, you have a bigger confidence that you are going to arrive on time. So it's like to give you like more space in here. So any point that is in here is probably going to be classified positive because it's very far from the margin. But if we went in here, for example, in this one, a point in here will be classified as a circle. But if you use your human knowledge, you will say, well, I don't know. You don't feel confident. You don't feel comfortable with such a decision. Yes or no, or you disagree?
I agree.
Yeah. You mean you agree that you are not, if we classify something in here as a circle, yeah, you don't feel comfortable with it.
Don't feel confident, no.
Yeah, you are saying, well, we are deciding about over that line, but I'm not sure. But this line, you will be more comfortable with anything classified here as a triangle or here as a circle. You will be much more comfortable. You can see that it is always closer to its siblings, whether triangles or circles. So this is the intuition, how the SVM started the formulation. Okay? So, well, yeah, I want to separate as well with as much as possible margin measure of confidence. When we are going to do the neural networks, we start with like the smallest possible neuron, with what we call the perceptron. And there is like the first one of the most naive way of learning a perceptron. A perceptron is also just a line like that, but it finds any line. The first line that divides the space will be the solution. It doesn't care if it is a good or bad. So it will not do a good job. It can find the perceptron, the naive implementation, I mean, it has like a better implementation, can find this, this, or this. But the SVM will always find this. And it is convex. It's here, like we said last time, it's a convex problem, which means that it will always converge to this solution. So yeah, larger margin, lower complexity. It means like the model is simpler, and it's independent of the number of dimensions. Well, we are going to see this next. Let's go in here. So this is what we are trying to. This is the mathematical formulation. We can do it, but it will take us like a lot of time to find these formulas. They are simple actually. They are not that complicated. So we are trying to maximize this. This is 2 divided by the mode of the W is the margin. Is this the sigma? This is how we compute the margin between these points. And W is my hyperplane, this plane. It's the parameters. Like we said, I will draw again, just to as a recall. This equation is f of x or y equals what? A multiplied by x plus b. Sorry for my drawing, it's horrible, I know. This is A. This is A. So when we call it W, it means this is W0 or W1 multiplied by X plus W0. So W1 multiplied by X plus W0. And this is the formula. So these are the weights, the parameters of my model, what I want to find. So this is the weights, which are in here. This is the norm, simply the norm, how we measure the distance. And we want to maximize, so, and this is 2 divided by this is that margin, how we compute it, that margin, the sigma. Subject to, this is just a constraint, we want to everything classified in its right place. So whenever we have something that is over 1, it means it's classified in the positive class, and things that are smaller than -1, they are classified as negative class. So we want to classify everything accurately. This is what this means. Maximizing the margin. We want to maximize the margin that allows us to classify everything accurately. To make it simpler, we want to find the hyperplane that has the highest margin possible. This is in a human like a language, in a human terms, not mathematically. We want to find the hyperplane or the line that has the maximum margin, and this is the constraint now, this constraint, and is able to classify everything accurately, meaning accurately that everything will be in this zone or this zone and nothing in here. This is what -1 and +1 means. Anything that is between -1 and +1 will be in here, will be inside. And in the SVM, we don't want anything to be inside because we want the margin to be empty. This is what the margin means. There is nothing inside. So we want the line or the hyperplane that has the maximum margin and is able to classify everything accurately. Here and here, and this is the margin. Do you understand what I just said, please? This is very important.
Yeah.
Because last time I didn't convert it like in human-like language. When whenever you see a mathematical formula, that was my way of understanding like quickly things in machine learning. Whenever I found a mathematical formula in a book or in a course, I translated it into a human language. That was like that's always what I do naturally, and it helped me to quickly understand most concepts in machine learning. Really, like most concepts, I applied this way of understanding them. Once I convert it, it becomes like very easy to absorb. Okay, guys.
I have a question on
yes.
On the previous was it the previous slide? I think where you have the maths formula.
A second. Or this slide, you mean?
Yeah, exactly. Sorry. You know, you have if yi is +1 and if yi is -1. Where's yi here?
Look at your class that you want to predict. Y is a regular Y.
Okay, yeah. The dependent.
Yeah, the dependent variable, exactly. It's what you want to predict. It's the last value of your data set. Like for the Batman example, if you remember, what we wanted to predict if he is a good guy or a bad guy.
Yeah.
This is the Y. And this is, well, we can do it later. This is how to predict what is the Y. What we call Y hat. Y hat is the predicted Y, what the model says, and the Y is the real Y, what we observe from the data set, from real life. Here we just did +1 and -1 because it's easier to formalize. +1 is one class and -1 is another class. Before we did 1 and 0. You can do just two different numbers that you can do anything, but it's easier to formalize with the SVM that way when you do +1 -1. So maximizing this, we are just going to convert it, is equal to minimizing this. Maximizing 2 divided by this is equal to minimizing this, because this is the invert and the square, and this is a distance. We do that because the problem becomes a quadratic equation, a quadratic problem, and a quadratic problem is always convex, like that. So if we want to minimize this, it is a convex problem, a quadratic problem. We just use the gradient descent and find my minimum. And we didn't change anything. This means we just merge these two formulas, this and this. We have these two conditions. This Y is +1 and this one is -1. If we multiply Y here and here, we can merge them because this one is positive. So if we multiply it, this will stay superior or equal to 1. And if it is negative, this will change. It will become superior or equal to 1. Like when we multiply something negative here and here, it becomes positive. So this one will be changed, and we would end up with the same formula here and here. So this is just to make things simpler. We just multiply this Y here and here, which allowed us to merge these two, superior or equal and inferior or equal, into one formula.
So Rida, are we multiplying the real Y, like the Y with the predicted one, Y hat?
Yes, exactly. We are multiplying them just to make them into one formula. To make them into one formula. So this, because it's easier to play with one formula rather than two, and you have to look if it is +1, -1. It's much easier to play with one than with two when we do optimization. So we are trying to minimize this with this constraint, and it is convex with just one minimum. So this is how it looks like. The margin, let's remove it. So this is the margin, the formula of the margin. We can prove it mathematically. You can find any book or anything that tells you how to why we ended up with this. It's very simple how to derive it mathematically and compute this margin. These are the support vectors. This is kind of an error. This is why we do it. I think I should have done this slide a bit later. Let's see if I can do something and then come back to it. Okay, let's look at it again. So this is the SVM, like how it is formulated. We are finding this hyperplane that has a maximum in here and is able to classify everything accurately. Of course, nothing will go beyond the margin. We don't want anything to be inside the margin. If this plus goes inside the margin, then my margin will become smaller. It will become smaller. So these points will define my margin, and we want a hyperplane that has the maximum margin, classifying everything accurately. But sometimes, sorry. For example, here, I want to go give you some time before moving in. Do you have any question, guys, before I move forward?
Just the one on the math slide again, the previous one, I think. How did you get from the first line to the second line? So all the equivalent problem.
From here to here?
Yeah.
I just multiplied this y here and here. I multiplied them. So if I multiply this y,
yep.
Let's have two formulas. So this is two formula. If I multiply this y with the first formula, nothing changed because this y equals 1.
Yep.
This y equals 1, so nothing changed. 1 by here and 1 by here. And if I multiply this y in here, this becomes 1.
Sign changes.
This is minus 1, but the sign, this one changes.
Yeah.
And it becomes the same formula, y multiplied by this, y here multiplied by the same. This y is plus 1, this one is minus 1, multiplied by the here. And here it will become exactly the same, superior or equal to 1, superior or equal to 1. So it's the same, basically the same formula. So we can merge them. We can keep only one.
And the
so and this is what
the max of 2 over the norm of w, that becomes a min of.
Yeah, because I just inverted it. I just even maximizing this is equivalent to minimizing this because this one is inverted.
But why the square? Why we put the square in there?
The square, yeah, we wanted it to become a convex problem with one minimum, like that. This one is generally positive. It's always positive because it's a distance, it's a norm. A norm is always positive. So when we invert it, it's again it's like the invert problem. But just 1 second, why? There is probably another reason. I want to see. There is probably another reason for the square, I think. Not just for the. Well, this will help us a lot when it becomes convex like that, because it's a square. And it is also, it's still an equivalent problem. Minimizing the maximizing this is minimizing this. I think let me have a look. I think there is another reason. Let me have a look. Yeah.
Maybe when you compute the norm is like the root square, and then when
possibly, but not necessarily. Yeah, we can use the square root indeed, but this is also the square root as well. Yeah, this is possible because if this is always positive.
Reda, could you say that because we have negative values, in order to make all of them positive, we square it to have positive values at the end?
Yeah, but this one is also positive.
Maybe because the theory of Riemann, I think something such that the term of 1 over x and 1 over x squared is same term. Is that
No,
they have the same limit?
The same what? Sorry.
The same limit. Do you remember the theory of Riemann?
So if this one, I
they
don't really remember them. So, but this
they
is
have
not
the same term, 1 over x or 1 over x squared.
Yeah. I still need to have a look. It looks very simple. I still don't find that if there is any reason beyond making it convex. But let me have a look. There are many aspects of the SVM I still don't master. From time to time, I find a new concept that I never heard of. I'm always surprised by this model, by the way. But there is a probability that there is another reason, not just to making it convex like that. Because well, these two we don't need it, yeah.
Yeah, because just like maximizing the first one means minimizing W, like would be enough. Yeah.
Yeah, indeed. Yeah, that's what I'm thinking of. Like maximizing this is minimizing W. Would it be enough? Yeah. Is it? I think we have to look at the maths here. So if we have this function, say this is the W norm, 1 divided by this would look like, it's like the invert when we divide 1 by this. It becomes something like, yeah, this is what we need to understand it. 1. Can anyone remember how 1 divided by x looks like? Something like that, I believe.
So it's asymptotic on the, yeah, exactly.
Something like that.
Yeah, yeah.
So yeah, maximizing this will go to infinity, and maximizing and minimizing this will still go to infinity. Of course, we are taking only the positive side, and it will also go to infinity. It's still the same, and minimizing this will go to 0. Yeah, so it's not exactly that. That's true. Now, by drawing it, I can see it better. So this is my function. So if I want to maximize it, I have to go to 0. This is the maximum. And maximum. And minimizing this, I'm going to infinity, because this doesn't go like to minus infinity. It's always positive. And this one, but this one divided, well, we are looking at 1 divided by and the x norm, the positive one. So if we go to 0 here, yeah, it is. Now I can see it clearly. Thank you, Salsabir, for your help. Now I can see it clearly. It's the same. So minimizing this, we are going to 0. This is the minimum. Sorry, maximizing. This is the maximum. Yes or no, guys?
Yeah.
Yeah.
And so maximizing this will go to 0, and minimizing this will also go to 0. It's the same problem. But if we do something like that, x squared will be something like that. This is the normal x. We are looking only at the positive side, of course. This is the normal x. And this is the x squared that we are trying to minimize. They have like the same limits. Yes or no? They have the same limits. But this one has a better gradient. You can see that the gradient here is like that. And the other one has a gradient like that. So the gradient here it's steeper. It allows me to go quicker. And then starts when we reach the when we are like that, this gradient is steeper. It's like if you what I mean, if you put a ball here, which one will be faster, this ball or this, or the ball running in here?
Can you repeat the question?
If I have I put a ball in here, let's say we have like a surface like that. I put a ball in here and a ball in here. Which one will be quicker to reach the minimum?
The gradient.
The one with this gradient, because this one is steeper. This one is like a normal gradient, like that. Although by the end this becomes a little bit better. But this one, if we start in here, we'll converge quickly. We will go to the minimum quicker than this.
Okay.
So I think it's probably the reason as well. It will converge quickly. I would like to look for it. I think that's probably the main reason. If we look at only the positive values of this function, of this, then we are going to probably find that minimizing this or this until 0 is the same problem, but this one will converge faster. That is what I'm thinking right now. I can search for it. Maybe you can find something better. Are you happy with this explanation, guys, or you feel confused? Even more confused than before. If you find it confusing, just forget it. It's not that important that you understand it at this level. You can understand it later, but for now, what I want you to understand is this: that we want to find a hyperplane that maximizes this margin and classifies everything accurately, and nothing goes inside the margin. This is what this formula means. This is how a human would read it. We would read this formula. Margin maximization. So now, guys, are you happy with these explanations? I want to make sure that you are all happy. If anyone is not, please let me know. It seems everybody is
Hello,
happy.
Reza.
Yeah.
I'm sorry because I'm come late for that. I can't get it, but it's I think it's okay. You can.
Okay.
You can move to the next point, and then maybe after I will.
Okay.
Get it.
Okay. Feel free to stop me or. Okay.
So what's slack variables?
The slack variable. Now it's I'm going to explain it. That's the other point. So let's say that I'm using a regular SVM, and I have these data points. So what line will be found in here? Which is the line that I'm going to? Where is it? It will be something in here, something like that. So this is the first part. The second part, approximately, it will be something in here. Yes or no? Are you all? Do you all agree with this?
Yes.
Yeah. So it will be something in here. But data sets are never perfect. When you collect data set, you can find a lot of problems, and it's really a lot. Sometimes measurements is not good. Sometimes you have like some data points that were measured in different circumstances, slightly different ones, and you end up with some noise, something in here, or something. One point here is misclassified. So here we can even, let's forget this point for now. I'm going to return to it. So when you see such problems, you can, maybe you would say that if I ignore one of the points that are close to the margin, I might end up with a better hyperplane. You would say that if I ignore this doesn't seem to be like a good point. Maybe it has some errors. We can't know in advance. We just test and see. Maybe if I ignore it, then I can end up with a better hyperplane, something like that. And the margin, of course, becomes better. It has some error. This is considered as an error because it violates the margin constraint. It is going inside the margin. We want the margin to be empty. But here, this point is going inside the margin. So even if it violates and we see that the accuracy, the overall accuracy is increasing, then we say, okay, let's tolerate some errors and see if we can generalize better. This is what is called, what we use, the slack variables. The slack variable is just the points that violates the constraint. This point and this point. This one goes inside the margin. It's still classified correctly, but it goes inside the margin, which means that the confidence level will be bad. This point is even a higher violation. It's even misclassified. It's going in the other class. Because simply we can't find a hyperplane that divides this data set accurately. We cannot in this problem. Like no hyperplane can divide because this point is in between these 4 dots. So we can't. The slack variables tolerate some errors, allows us to tolerate some errors. So, for example, we have this value. How we compute the slack variable by this. If it is between 0 and 1, the point is between the margin and the correct side of the hyperplane. So if it is between 0 and 1, it means it's inside the margin, but it is still correct. But if it is above 1, then it is misclassified. This is how we compute the slack variables. So we introduce them in this formula. We are going to introduce them to this formula. These slack variables, we are going to put them inside this formula to allow some error to allow the algorithm to be error tolerant, more error tolerant. So how it will look like? So this is it. We are still optimizing W squared, the norm of W squared, plus the sum of the slack variables. Here we have, in this problem, we have only 2 slack variables. All the rest are 0. These are 0, 0. There is no error. Here there is a positive one between 0 and 1. This is the slack variable in here. And here it is a higher one. It is above 1. This is a higher error for this slack variable. So instead of optimizing only this, finding like the margin, the biggest margin, we add this, we add the sum of the errors, and we multiply them by C. C is just a number that you put to say, is it like this error, are they important or not? So if C equals 0, if C equals 0, it means that we don't want to see this error. This error are not going to affect anything. So we don't want C equals 0. It means, sorry, just 1 second. Yeah, if C equals 0, it means that we tolerate a lot of errors. We tolerate a lot of errors. And here we put 1 minus this. This is like so the constraint that we want to optimize for.
Rida,
yeah?
please, what is the purpose of calculating the slack errors? It's like to see how our SVM or hyperplane handle the, I don't know, it's like the errors or what?
Yes, we want to see if our hyperplane, like to give it some tolerance. if the hyperplane, we don't want any error to be happening. If we don't want any error to be happening, my hyperplane will, and we ignore this. So my hyperplane will go in here. Will go in here. So what we want to do is to allow to, when the hyperplane, what it will do, it will compromise between finding the maximum margin and minimizing the errors. There is like a compromise between the two. So here it is trying, when it minimizes this, it is trying to find the maximum margin, but at the same time, this error will drag this value. So it's like the same, like one driving the value. So this W's will drive the value of having a maximum margin, but the errors will also drive the value to the other direction.
So I see.
The higher the error, the worse the outcome. So when we minimize this, we are trying to minimize this part and this part, both of them, because it's the sum. We are trying to minimize this. If we minimize this, we get the highest margin, and if we minimize this, we get the lowest possible errors. I want some output from you, some input from you guys to see where you are. I have a feeling that you didn't get it fully.
So it's like if we don't allow, the slack variable, that means we cannot have the best hyperplane.
No, we can still have the best hyperplane, but we do not tolerate any error.
Okay.
We are not going to tolerate any error. When we introduce the slack variable, there is I want to explain this before. There is two versions of the SVM. There is the hard margin SVM, and there is the soft margin SVM.
Okay.
The normal one, what we studied right now, for example, this is called the hard margin SVM. The hard margin SVM, just look at the data set and find the best hyperplane. If we at that point, there is even no best hyperplane, because this constraint will not be correct, because for one value, this won't be like acceptable. This will be false, because for this point, for these 2 points, or for this point, sorry, this constraint will not be observed, because it's misclassified. We cannot never classify it accurately. Yes or no?
Yes.
So we can never classify it accurately. This concept cannot solve this problem. So what we use for this kind of problems, the hard margin SVM is here for linearly separable problems, only linearly separable problems. But when the problem is not linearly separable, we need the soft margin hyperplane, and it has two tolerance way. It can tolerate misclassification or ignore some certain points that are too close inside the margin. Like I said, the SVM try to build a margin with nothing inside. That is the hard margin SVM. Nothing should come inside. Are you happy with this explanation? With what I'm saying, guys? I need some input from you. I really need to know if you are in the right track. The SVM doesn't tolerate anything, the hard margin SVM, anything misclassified or inside this. Inside.
So does that mean a hard margin SVM is not a viable option for this problem?
Yes, it is not, because it will never find a hyperplane that is able to satisfy the constraint.
Well, how does the formula for the hard margin SVM differ to the soft margin SVM? Or the...
Yeah, this is what we add to it. For the soft margin SVM, we simply add the slack variables. So and here the constraint is relaxed. There is a relaxation of the constraint. So it's not superior to 1, which when we say superior to 1, it means it is not inside the margin. This is what superior to 1 means. It is not inside the margin. But when we add this, so we tolerate a little bit of errors. It can be inside the margin by this slack variable amount.
So essentially, if we look at this formula, the one you've got now, and if you go back to the previous slide, I just want to understand. So that line where you have the margin 2 over W, the norm of W, essentially we're actually finding a line that's not there. I presume we're finding a line that's somewhere near the red dots or somewhere near the blue dots, but after that transformation is applied, it shifts to the middle.
Exactly, it shifts to here. But it depends on the C. It will really depends on this C. And you set it in the beginning. Generally, what we do, we put some values for C and we see which one is the best.
How do you get that best value?
Yeah, the C value.
How do you get that best value?
The hyperparameters. It's up to you. It's your experience. Generally, there are ways that we are going to discuss later, but there is no like best way yet. It's generally by experience, but in general, you can find a good enough C more or less easily. A good enough one. Maybe not the perfect one, but a good enough one. So then let's study this formula. This is to find, when we minimize this, we find the biggest margin, hyperplane. And when we minimize this, we want the minimum errors. So here we are doing the sum of the errors, but we are multiplying them by C. We are multiplying them by C. So if C equals 0, we are going to the hard margin hyperplane. Sorry, no. We are going to, we don't care about making any error. We are going obviously to make a lot of errors if C equals 0, which is not really useful. If we put 0 in here, and here we have still the tolerance, so we are tolerating, this is 1 minus the error, the slack variable. This is, I think, called she or something like that. If someone can confirm, is this she? If you
epsilon?
know.
Oh, that's shy or epsilon?
Shy, yeah, shy or shy. I don't know. One of this Greek stuff.
I think it's epsilon.
Yeah, it's one of the two. So if C equals 0, here we are still tolerating the error, some errors. So this will tolerate basically any error. But here we are going to like find in like any line that will maximize the margin, but we will make still a lot of errors, which is not good. But if C equals infinity, then we are not going to tolerate any error. Basically, this needs to be 0. Well, when we multiply 0 by infinity here, it's always 0, by the way. So if we put a very large C, let's say, we do not tolerate any error. We are going to the hard margin SVM if C is very large, because this one will be very big, this term, and anything that we modify in here can make this even bigger. So here we are going to not to tolerate any error. So this is, you don't need to understand it fully, just by instinct, guys. Believe me, a lot of data scientists I know don't understand this maths fully. I would say most of them. So just get the intuition, what we are doing. Just understand globally what we are doing. Later, if you want to understand this like deeply, feel free to do it. But I want you here to just understand the spirit of what we are doing. Are you happy with this? Like understanding the globality of what we are doing, not like the details. Anyone is not happy? Please speak. I really need you to speak. Even when you speak to me, I can quickly sense what's your concern, what part of what I'm saying you don't get. So just give me some input, because I can't even see your faces.
It's okay, Reda, it's okay. Just be keeping the generality of things.
Okay. And it is for everybody.
Reda, how about C? So if we put C as an infinity, here we are not having the margin, we are minimizing the margin,
We are minimizing them. Sorry. Oh.
If we
yeah, if we put C to infinity,
to infinity,
so it means that this one is very important.
Yeah, it will be very important. Means
it will become much more important than this. And this
so
is
here. So we will violate the margin.
Well, if we will not violate, I don't know exactly what you mean by violate the margin, but if we put this to infinity, it means that we don't want to have any error. The algorithm will not make any error, but it's still an optimization problem. For example, in here, it means we don't care about the size of the margin. If we put this to infinity, we don't care about the size of the margin. We just want a hyperplane that divides things optimally.
Okay.
Like here. For example, in here, I would say the best hyperplane, if we don't care about the margin, size of the margin, because the second part is how many misclassification we made. It will be something that minimize this. So it will be very close to here, probably something in here, a line in here. That is very close to this point, because we want it to be as close as possible to this line, so this point can go in here, but we can't really do that. We can just get very close to it. So we are going here, something in here, somewhere here. If we put C to infinity, or I mean a very big number when I say infinity. So this is what we call the soft margin SVM, and in practice it is the one used instead of the large margin instead of the hard margin SVM. If you want a hard margin like SVM, you just need to put a very large C. If we want a softer one, you just put a smaller C, 0.1. 0.1 we tolerate, for example, some errors in here because it's a factor that we multiply. It will tolerate some errors, but still try to find the best hyperplane that maximizes the margin. So here we have these two errors. So here, this sum, just to make it simple, this sum equals to this divided by this, or this squared. This is the margin. So it's the invert of this plus this distance plus this distance multiplied by C. So these are the two distances multiplied by C plus W squared, which is the square root of the invert of the margin. So this is what we are doing. Again, guys, you don't need to understand it fully. You need here to understand the general concept. What we are doing is trying to maximize the margin, trying to violate just few points. We try to violate, and C determines how many points we are allowed to violate. It's like the coefficient. If C, like I said, is too large, we don't want to violate many points. If C is too small, we can tolerate more violations. Still, we are trying to maximize the margin. This is what I want you to understand. Only this. Don't complicate all of this. Put this complicated maths in your head yet. Just understand things by the human way, the human language style. We want to maximize the margin, tolerating some errors. How much we tolerate the errors will depend on the C. This is a very simple, simplified explanation. I guess that you should be all happy with this.
Yes, very good.
Okay. Once you feel that you could understand this explanation, then feel free to dive in the maths. Go there and see, draw your equations, how things are converging, how the optimization works. It will make your understanding even better. But what you need right now is just to understand in everyday language how we explain these things. We call C the regularization parameter. Like I said, small c allows constraint to be easily ignored. Large margin. Large C makes constraint hard to ignore. Narrow margin. C equals infinity enforces all constraint which we call the hard margin SVM. So can anyone tell me what's the difference between hard margin SVM and soft margin SVM? This can be easily an interview question when you apply for a job. Can anyone tell me?
A hard margin SVM doesn't accept any errors, any misclassification, and the soft margin it does accept errors, so it ignores some points so that it gets a larger margin.
Yes, and by how many like points it will ignore?
Sorry?
How many points, how many error can it tolerate? Is it all the error, just few errors?
It depends.
On what?
It depends on the C that we made, no?
Perfect, perfect, yeah.
On the C?
Exactly. That's the explanation I would like want to hear during an interview. That's the explanation I would like to hear in an interview.
Okay, thank you.
So it's still a quadratic optimization problem, which is good, and there is a unique minimum. Even like when we add the slack variable, it's still quadratic. There is only, and what is good, it has only one parameter to set. The hyperparameter, I mean, only C. So this is for the soft margin and hard margin SVM.
So can you repeat the answer again, please? Just
yeah,
the difference.
The soft margin, that's the hard margin SVM, does not tolerate any error. It wants to classify everything accurately. It finds the hyperplane that classifies everything. It still maximizes the margin, but it wants everything to be classified accurately according to the training dataset. The soft margin SVM can tolerate some errors. It tolerates points inside the margin, and it can also tolerate points misclassified. How much it will tolerate depends on C. The bigger the C, the less tolerant it becomes. The smaller the C, the more tolerant it becomes. So if you put C equals 0, it will not look at anything. It will just get the highest margin, the biggest margin, and it may misclassify everything, which is not really useful. If C equals infinity, it goes to the hard margin SVM. Are you happy with my explanation?
Yep.
Yeah, perfect. Sorry. Just a question. Is the cost in the function SVM in the R?
Is it, sorry, what?
The cost?
The cost function. This is the cost function.
I mean, when you no, it's not this one. It's when you program in the programming. That is the function SVM.
Yeah, you don't need to touch it. This is like self-contained in the program. You just supply, when you program, you just supply your data set to the SVM. You set the C, and you let it find the hyperplane because it knows all these details.
Okay, so this C is the same C in the function in the programming.
Yeah, it's the C exactly. It's called C in most libraries.
Okay, thank you.
And then we have the kernel. We are going to look at what is the kernel next. Okay. What time is it? It's okay. I'm going to look at what we call the kernel. So in the hyperparameters, you have the C and the kernel. The kernel can also have other hyperparameters. You know, like applying that programmatically is much easier than understanding what you are talking about here. Programming, programming it is much easier. So, this is. Yes, Najwa, what do you want to say?
I think here because we understood the constraints, but programming is just we use the API.
The API, yeah. But what is bad is that in programming, if you don't know all these maths, you don't know what is happening in your classification when you do the programming. For example, you put C, value in C, and you see some accuracy value, but you don't understand it. Why increasing this C can make things better. Decreasing it make things like less good. So you don't know what is really happening. But when you understand all of this, like you look at the kernel, you look at the C, you can build your intuition about what is happening and what your data set is about.
Rita, just a question. In soft SVM, for example, we have how we can detect, for example, we have like 3 errors or 2 errors. Or
I think
the
libraries can give you that. It's very easy. You just compute the classification value and of each point, and it will tell you if it is well classified or misclassified. So you can easily compute that. I'm sure libraries will do it for you. Will give you the misclassifications and the number of slack variables used. So this is an example. No problem. This is an example. C equals 10. So we ignore this point. What happened? It really depends. You don't know when you say C equals 10. You don't know how many points are going to be ignored. It's because it's like two terms that we are trying to optimize, and we don't know how C is going to affect the sum in advance, because there are many points that you just apply it, put a C, and see what is happening. When we say C equals 10, it doesn't mean that we are ignoring 10 points or so. It's just a value inside the formula. The number of points that will be ignored is determined after computing the whole thing, or the cost function that we are trying to optimize. So here in C equals 10, we just got one ignored point in here, and the margin became bigger. And these are the support vectors. We say when we put C equals infinity, this is the hard margin version, we got this hyperplane instead of this. To say if it is better or not, you just need to use the testing data set that you didn't use for training. But set some data points that did not exist when you train. Some new points. We are going to use them next time. In the next session, you're going to try them and see which model is doing better, this one or this one. Generally, this tends to do better because we ignored only one point and the margin became much bigger. We didn't ignore a lot, and the margin is much bigger, which looks from an intuitive point of view looks better. Okay, so this is the formula that we were looking at, subject to this, and this is the constraint. So this is just we just did like combine this with the constraint. So this is a regularization. We combined both this and this. We can combine them in here in one formula to make it easier for us. But don't worry about this yet. This is something quite important now. There is what we are studying so far in here is the primal problem, the primal formulation. Well, that's what we are trying to optimize. We have what we call the dual problem, dual formulation. And this is a very powerful concept. I need you really to focus a lot in here. So we have the primal problem that we were studying, and we have the dual problem. The dual problem looks like that. We want to maximize this, the sum of alphas. This is not exactly the parameters that are like in the W. These are a little bit different. -1, this is the same alphas what we are trying to learn. These are yj and yk. What is y? What is y, guys? What is y?
Error.
The real function.
C.
Yeah. No. Y is what we want to predict.
Oh, the independent.
That's just a dependent variable. We always call it y. Yeah, we always call it y. So we are multiplying each two y's yj and yk, it means one of the y and one of the other one. So each 2 data points. We will multiply in the y's of each 2 data points, and xj and xk are what? The x's. What are the x's?
The entries. It's like
exactly. It's the parameters. Sorry, not the parameters. It's 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 the entries exactly.
Yeah.
Like in Batman, we have mask, we have ears, we have these are the axes. And the y in the Batman example is bad guy or good guy. And the axes are the features, what we call the features. How the shape of the ears, the mask, I don't know, glasses, I don't know if it's even exists. So these are the features. The features are the entries to the system. And y is the dependent variable, which is what we want to predict. So we are just multiplying them, y by y, and each point by another point. And these are vectors, of course. xj and xk are vectors, which means multiple values. So just to give an example here, I want to give you this. So this is the y, good guy or bad guy, and these are the x's. x1, x2, x3, x4, and this xj, xk, this is xj, 1 is xj, this is say xk. Normally I should not call it xj, is because it's a vector, it contains many things. So this is for example, Batman, xj is Batman, and this is Penguin or Robin or whatever. So this is for Batman, this is for Robin. So we multiply them because they are values. We multiply them, and we multiply also their y's, and we do the sum for all points. So we do every combination. So we maximize this, and subject to alphas if this is between 0 and c, and alphas multiplied by the y's, their sum equals 0. So this is equivalent to this. Don't tell me why. We need to dive mathematically very deep to find out why this equals to this, and it will probably take us a lot of time. Not one session, maybe one session, but a very long one. So this is equivalent to this. What is good about it? Here, the number w depends on the dimension. How many w's we will have? So because it's a hyperplane, it will depend on the dimension where we are. So if we are in 2Ds, w will be 2D. We will have 3 actually, plus the intercept. A, B, plus C. So when we are in 2 dimensions. So actually we will be we are going to divide some with one line. Actually, when we have 2 dimensions, it's 3D. So a line like that will have only 2 parameters, A and B. This line. It has 2 parameters. So if we are in a higher dimensional space, this W will scale accordingly. So the more dimensions we have, the more complex the problem. It will take us a lot of time to find the W's if we are in a very high dimensional space. If we are, for example, in 1000 dimensions, it will take us a lot of time to find all 1000 W's, because this line will be in like 1000 dimensional space. Here, we are not doing that. We are trying to find the alphas. And the number of alphas depends on how many examples we have. So if we have a very high dimensional space, we should use the dual problem. If we have small dimensional space but a lot of examples, we should use this, the primal problem. Because the primal problem depends on the dimensions. So if you have 3D and 1 million element, this will do things in a very good way, because this one will still need to compute things, but it will do okay. But this one depends. Sorry, if we have a very high dimensions, this will not do a good job. I don't know if I said this or the opposite. So if you have a higher dimension, this will make it very big and very hard to optimize. It will need to find more points, a lot of more parameters, A, B, C, D, which are the W's. But if I have still like this higher dimensional space, this one will do better, because we need to find alphas, not dimensions. And alphas depend on the number of points. So these are JK, are all my points, my data points, this one in here. And each one will have its alpha. So this one depends on how many points I have. To make it short, when you have a lot of dimensions, use this one. When you have a lot of points, which means higher, more than the dimensions, use this one. The primal problem, the dual problem. This will be easier to optimize depending on your case. Are you happy with this? With what I'm saying, guys?
Yeah.
Yes.
Yeah. This is
Reza, may I ask dual problem, is that to have like a correlation between the data sets because it's so large? No.
No, it's not for the correlation. It's just quicker to optimize a dual problem. To optimize a dual problem when you have higher dimensional space, because it doesn't look at the dimension. The dimension will not affect. What will affect us is more the number of samples, because this, what we are trying to optimize. One second. What we are trying to optimize here is the W's, and the number of W's will tell us how long it will take us to optimize it. Okay, so what we are going to do is, it will take a lot. But if here the number of dimension is high, this doesn't depend on it. It depends only on the points, and they are equivalent problem. We are trying to, at the end, we will find the same solution if we put the same C here.
Yeah, I'm sure that we would have same solution, and for that, maybe how to reduce the dimension. Arbitrary.
Yeah, here we are. Yeah, you will use the one that is quicker to optimize, depending on your case. So here, if n, the n is the number of examples, d is the number of dimensions. If n is smaller, much smaller than d, then it's more efficient to solve for alphas than w's, which means a dual problem.
Okay.
So this is for the dual problem. I think this was, what if it's not linear? Now let's see if the problem is not linearly separable. Shall I give you a pause, guys?
Yeah, it would be good.
Okay.
Yeah, we need it.
Okay. You can have coffee this time.
Yeah, coffee and everything. Cakes.
And probably you've got a lot of cakes ready to to take care of.
I saved stuff for you on the freezer.
Okay. Let's have a quick pause. Like, not a quick, you can have. Okay, I will give you 15 minutes this time.
Nice.
Amel, I know her.
Okay, see you in, say, 15 minutes.
Okay, yeah.
Okay, guys.
Thank you.
This conference will now be recorded.
So, So yeah, now so yeah, what if the problem is not linearly separable like this one? We can use the slack stuff, the slack variables, and try to ignore with the C, put in the right C. It will allow us to ignore this triangle. But what if we have something like that? So we have circles here and triangles here. There is no C that can help here. Yes or no?
Yeah.
There is no C that can help in this example. Any C will ignore a lot of stuffs. Do you agree or not, guys?
Yes. Yes.
Yeah. Any C can, any hyperplane is bad. This one, this one, this one. Any hyperplane will do a poor job. So what we do, so even with the slack variables, the job will be very bad. Like in here, yeah, nothing can really help. So what we do, we use the kernel. We use this kernel. What is a kernel? Let's just see what is a kernel. A kernel is something that allows us to move from 2D, like in here in this example, into a higher dimensional space. So this is 2D, and this is what? Unmute yourself, guys, speak.
The 3D.
Yeah, 3D. Just simple 3D. And we just computed another dimension. So here we have x1 and x. It's a function, yeah. x1 and x2. x1 we just squared it. Y we just also squared x2, which are more or less the same now as x1 and x2. And z we computed it like this way. 2 square 2 multiplied by x1 multiplied by x2. And so we got something like that. Like the space was warped. You can see that the space was flat in here, but here we just took it from the middle and stretched it like a cone, like what is happening here. Now, when we do that, we can find the separating hyperplane. In 3D, it's a plane. It's not a line. In 3D, we have this plane. So we could find this plane separating this space. And it can really gives a very good like separation. Can really give some excellent separation like in here. So this is the kernel. It's not the kernel trick yet. So what we are doing, how would you implement it if we are you are in here? What would you do? We want to optimize this formula with some slack, you see, to allow some error to make it error tolerant. What would you do to make it work like how we want? To add this kernel, what would you do? If you can answer me, I buy you a trip to China. Please, guy, any error, any mistake, feel free to make any mistake.
We change the plane.
So we want, well, we have this problem. We have this problem. And we want to apply to it the SVM, which is this formula, but with the kernel. We want to move to 3D. So what we are going to do to make this go to 3D? From 2D to 3D, what are we going to do? It's a simple, very simple question. Don't complicate it.
We need to square all the values, something to get a high.
We just need to modify this x. So x is 2 values. This is the values. We don't change the y. The y is still always the same class. X has 2 values. x and y. So we just modify it. It becomes from two variables, two values, x and y, x1 and x2, sorry, to x1, x2, x3. And we compute the new vector. Instead of two values, it will have three values. That's all what we do. And we still, so we compute the new three values, and we go here and we apply this formula, and we get a hyperplane. Instead of 2D, we get something like this. Yeah, we transform the variables exactly like in here. We had x1 and x2. We did this, x, y, z, and the problem shifted to this, and we apply the regular formula to it. This is one way of doing it. This is one way of doing it. But if we have a lot of points, a lot of data points, we are going to transform all of them. Yes or no?
Yes.
Yes, of course.
All of them. And sometimes moving to one extra dimension is not enough. We need to move to a much higher dimension. From 2 maybe to 1 million sometimes. Well, it's not always good to move to a very high dimension, but sometimes we need to move to a very high dimension. And this means that we need to compute a lot of terms. We need a lot of computation for all the new terms that we are going to compute. Like in here, we call it phi, this phi. We are taking x1 and x2 and transforming it into how many here? 6. We have 6. This is a polynomial kernel. This is called the polynomial kernel because we just squared this with degree 2. Squared this, multiplied them, and well, we just added this coefficients. Polynomial kernel will just take things to this kind of computation, to the degree 2. So here we ended up with 6 values. So it's clear that we need to compute a lot of things. But we said, this is if we want to use the primal problem, the primal formulation, sorry. If we want to use the primal formulation, we are obliged to compute all the new points. But with the dual formulation, now let's go to that's why we want to use the dual. We said that the dual is good when the dimension is small. The dual formulation does well when the dimension is small. But if we go to the high dimension, yeah?
The dual, we use it when we have a high dimension, no?
No, when we have, sorry, yeah, the
Yeah.
dual. Yeah, sorry, I mispronounced. The dual, exactly. You're right. Thank you. It means we are in a good direction.
We got confused.
Yeah, I got confused. Sorry. So the dual, yeah. The dual is when we have high dimensions, the dual is not affected. It is affected only by the number of data points. So we can go to very high dimensions, and the dual still is not going to be affected. But there is something more, much more powerful than that. This phi is the new point that goes from this to this. So we need to replace them. X, J, and Xk, we need to replace them, obviously. Yes or no, guys?
Yes, yes.
You are happy with this? But what we are doing here is the dot product. What we are doing in here, no, it's kind of more complicated, but it's in reality it is less complicated. We don't need the points themselves. We don't need these 2 points themselves. If we can jump from here to directly the result of the dot product, we won't need to compute this. If we find a magic way that allows us to jump from this product to the result of these dot products without computing this and this. If we find a way to do that, it will save us a lot of computation, a lot of computational time. And this is the kernel trick. This is what is called the kernel trick. The kernel trick is that we are able to compute this without computing this individually. We don't need to compute this individually to get the final value. We just need these two things. And we can,
how we can do it?
Yes, yes. We can do it like that. We call this product K, the kernel function. We call it K, Kx Z, or yeah, Z. It has some, I don't want to dive into the math. It has to be symmetric, so positive semi-definite function. Is Mercer's theorem. You can have a look at it. I don't want really to dive into these mathematical proofs right now. I don't even think it's a good idea for the moment. So this dot product, it's a formula. The K is a formula that is studied. How to put a good formula is a difficult thing. But we have found few very good formulas that allows us to move from XZ and compute directly the dot product instead of moving to the higher dimension and then computing it. Like the polynomial kernel, the Gaussian kernel, it is also called the RBF kernel. These two kernels are very famous. These two kernels are very famous. Let's move in here. This is the linear kernel. Actually, we are not doing anything. The linear kernel means that it's like kernel-less SVM. It's the regular soft margin SVM if you are using the previous formulas. Polynomial kernel, we do this. 1 plus x multiplied by x, the two x's. This is just for a notation. Don't worry about this t, because we are dealing with matrices, not with vectors. So we do this t. This is just see it as multiplying the two data points. Power to d. Once we compute this, only this, we multiply them. We put the power to d, and we are not doing anything. We only compute this, and it's just numbers. And we do the plus, and we just put it to power. It's very, very quick to put it to something to power computationally, and it is equivalent to that polynomial kernel we saw before here. So we did not compute all of these terms. We just did this multiplying just two things. It's just one extra step compared to this one. Multiply this plus 1 is very quick, and we just put it to power d. This is just one extra operation for any d bigger than 0. And it with just one extra step, we are doing as well as almost as fast as the linear kernel. This is the magic.
It will be equal.
Equal to what? Equal, yeah, equal to this.
To the past.
Or this. And of course, we multiply them again. We compute all of these terms. It's not exactly this. It's going to be slightly modified. I'm not sure if it is exactly the same, but this is it.
Okay.
And this is what happened. Instead of going to the higher space, we did x multiplied by z plus 1 power to 2. So this equals to this. So we don't need to compute all of these terms. Just this is enough.
Okay.
So we are computing the dot product without moving to the higher space. And this is almost as quick as computing x multiplied by z. It's almost as quick. It's just one operation extra. And then we have the famous Gaussian kernel. This is a bit of a crazy kernel. Instead of, this is the polynomial kernel. D is the dimension. Generally, the order of the new dimension depends on this size plus 1 power to d. So if it is like 3 dimensions here, it's 4 power to, and we are dealing with a kernel on dimension 2. It's 4 power to 2. It means 16. It's something like that. It's not exactly that, but just from memory, it's something like that. It's moving from, if we are having 3 dimensions and d equals 2, we go to 16, something around that number. I might be wrong here, but it's I'm probably very close to it. So we move from 3D to something very close to 16 dimensions. But the Gaussian kernel moves from your dimension, 3 or whatever you have, to an infinite dimension. Some people say it's theoretically infinite. It's not. It's really infinite. We are moving from 3D of whatever dimension you have to an infinite dimensional space. It's mind-blowing. Like you can't. We are not normally, in normal cases, we should compute 1 million terms, or not 1 million, infinite terms here.
How would you compute that if it's infinite?
We are going to see it. Normally, if it is infinite, we have to compute infinite terms.
Is that infinite by definition, or is that infinite by has it been proved to be infinite, or is it just?
It is. Yeah. I will explain it. I will explain why it is infinite. Normally, if we are using the primal formulation to do it, we need to compute infinite terms and then do the dot product or whatever we are doing. Well, computing an infinite series, infinite vector, is impossible. But still, because we are using the kernel trick, we can compute the dot product of infinite terms without computing them at all, with just this formula. This is the first point. Second point, exponential of this. This is all what it is. This is all what it is. And if you look at this formula, you can find its expansion, Taylor's expansion, which is something like a sum of polynomials like this. It's a bit like, you can see it as a polynomial kernel with d equals infinity. You can find the mathematical proof for it. It's very easy. If you Google it, Gaussian kernel, mathematical proof, infinite dimension, you can quickly find why it is infinite. Because it is equal to this with d equals infinity. And their sum will converge to this value. You remember when we did before, when we did the sum of series, infinite series from 0 to infinity. We can, in many cases, we can find like one formula that can compute this series, the sum of the series. You remember this in maths modules. There are like many series that when we compute their sum, when n goes to infinity, we can find a formula that does it. This is the same.
Yeah, we call it the general term.
Something like that, yeah. We calculate something like that. The sum, and we get the general term for the sum. But allows us to compute our sum when n tends to infinity. This is what is really happening here. This is actually what is happening. So we are computing the dot product of infinite vectors. X and x dash are vectors, 2 data points. They are infinite, where the real x are not. But when we move to the higher space, higher dimensional space, they are infinite. But the dot product can be computed very easily, even in that infinite dimensional space. And we can go to very high dimensions. And this kernel, you will find it called Gaussian kernel or RBF kernel. You can also find this terminology, RBF kernel. It has one hyperparameter, sigma, but we are going to see what it affects. The polynomial kernel has the D. Of course, the linear kernel doesn't need any hyperparameter. So you need to set them first before using your SVM. If you are using a polynomial kernel, you need to set the D. If you are using the Gaussian kernel, you need to set the sigma. And let's see what's the effect of the sigma. The D is just the degree. The higher the D, the more complicated it will be the higher also will be the dimension, and the more complicated it will be. If we, just to make it simple, if we move by from xy, x1, x2 to like using a polynomial kernel degree 2. We just go from this. Let's say we go to one extra dimension. Degree 2, it means something like that. This is a degree 2, x squared. So points that were in here, let's say we had points in here, will go in here. Others will go in here and in here. And we can have here my hyperplane that can separate these points from these points. This is just an example of degree 2, moving from degree from these 2 degrees and then one extra dimension, that is x squared. Let's now, before that, do you have any question here with the Gaussian kernel?
Which one is better than others? How we can choose?
Normally you have to test. There is nothing but testing, but Gaussian kernels are very powerful. But one thing I want you to notice, we are moving to a very high dimensional space, infinite. Normally when we move to infinite, the more dimension we add, the lower the generalization. That's the general concept, because the model is more complicated. You remember we said last time, the more complicated the model, the worse it is in terms of generalization. The simpler the model, the better it is. So this kernel is going against the intuition. Do you agree?
That's correct.
Yeah, it's moving against it. It's going to infinite dimension in which we can have, like each dimension, we can put one of our points, for example, here. So we have, let's say we have 3 points. If we go, and let's say we are in 1 dimension, 3 points. So if we go to 3D, and we put each point with some kernel, each point in 1 dimension, then we can classify them all easily. Everything will be like separate them. If we can separate these 2 points together, or these 2 points together, it's very easy. When we move all the points into their dimension, things becomes like very easily separated. But it will probably not generalize well, because we're not learning anything. We are just putting a point, like we're just memorizing our points. So moving to a very high dimension is susceptible in making my model less general. However, which is the magic of the Gaussian kernel, it does not. We are moving to a very high dimension. I still don't know it why, to be honest. I have my assumptions, but I'm not sure why it is like that. With the Gaussian kernel, we are going to an infinite dimension, yet the model still generalizes well. Let's see how the sigma is affecting my model. It's really mind-blowing, this kernel. So this is an example. This example was taken from this guy's slides, and Rosie Selman. He has some really good slides about the SVM. I took quite a lot from his slides. So let's say we have these data points. Of course, the regular SVM, whether with slack or not, variables, it's not going to do anything good with it. We are going to use the RBF kernel, which is the Gaussian kernel. So if, well, we put C equals infinity, which means it is what? C equals infinity means?
The higher slack.
It's a hard margin.
Yeah.
Yeah.
It's the hard margin SVM. So here we are not like tolerating any error. Sigma equals 1. Make like this decision boundary. You can see it was able like to find very good like circle, which is a good classification, and it is smooth. You can see that it is almost like an ellipse, very good ellipse. Now let's change. C equals 100. It is no longer a hard margin. We didn't change the sigma. No longer a hard margin, so we tolerated 1 error. The SVM is no longer finding a hyperplane because, or a line. Sorry, it's not finding any line because the kernel is taking these points to a very high dimension and finding like a hyperplane. Imagine, say, like if we add something, if we stretch the space in here, and we add the hyperplane that goes below it, the separation will be like a circle. Yes or no? Did you understand this? Can you picture it? It's exactly like in here. What I mean, this is what is happening. This looks like a circle here. If we like project this in here, to go back in here to see how this plane translates in this space, it will be something. If we project it, it will be something, a circle around this. So it will be something like that. So this is what is happening, why we see a circle instead of a hyperplane, a line like. This is the effect of the kernel, like moving into the higher dimension and going back and see how my line or my hyperplane is translated into the two-dimensional space. Again, now what we used before, yeah, this is with 100. With 100, it's just adding some slacks, and it is ignoring this. We are ignoring this point, and these are the support vectors. Now, with 10, what happened with 10, guys? What happened?
Get more error.
Margin.
We ignored a lot.
Yes.
We ignored many, so many. This. We ignored. Maybe it's not good, maybe it's good. It's probably not that good because we ignored quite almost as many as what we have inside. So testing will tell us, generally when we test with the testing set that was not used for training, will tell us if we did a good job or not by ignoring that many. Now, this is the hard margin. Yeah, we did it. Sigma equals 1. Now we are changing the sigma. We are still with the hard margin, but we are changing the sigma. We are taking a smaller sigma. What is happening? This shape is following the shape of the support vectors, as you can see here. So this shape is not homogeneous, but it is affected by the support vectors. It's following them. Again, with more sigma, even smaller, you can see that the external shape is again following how the support vectors look like. It is following them. Of course, we are using C infinity, which is the hard margin SVM, and the sigma you can see. So it's building like a bump. It's a bit hard to explain here. It's building like a bumper in the higher dimensional space around each point. So each of these points will have receive a bump in the extra space. And because of it, when we draw the hyperplane, it will not be something as homogeneous as in here, for example, but it will follow like the support vectors bumps. It will follow them. So really, I see it as a magic model, especially with the RBF kernel. It's really magic how things goes. And of course, when we have very high dimensions in the beginning to begin with, not just 2 dimensions, it's very hard to visualize what is happening. But with 2 dimensions, we can visualize, go to the big space, and coming back and see how each point is behaving. So this is how making a smaller sigma will follow the shape, the external shape of the vectors. And what is the best one depends really on your use case. You can see that high sigmas equals 1 make a smoother boundary, smoother one. This is more simple, generally. It's a more simple, so it might generalize better, but only testing will tell you what is the best sigma. And here, you can see the sigma equals 0.1. It makes things not smooth, but following a bit the shape of the support vectors. And of course, testing will tell you try different C's, different sigmas, combining them, and you see which one does better. the SVM is, especially the linear kernel, is one of the best in text classification in NLP. Of course, NLP we're using deep learning does better. But before the advent of deep learning, the SVM was the way to go. It scales very high, very well in high dimensions. It's less prone to overfitting, for example, than decision trees. Of course, finding good kernels parameters might not be easy. So you need to try a lot of kernels values like the sigma or the D to find what is the best one. So this is just to make things clearer. So linear SVM can have hard and soft margin. C parameter decide whether we tolerate misclassifications for large support vectors. If C is small, the margin will be large, generalize better, but we'll have more misclassified example, etc. And if C is large, the margin will be small for a better accuracy, but may not generalize well. So thank you, guys. So we are more or less done with the SVM. I know it's a very complicated model, but I feel like it wasn't too tough. I feel like you got it.
A bit, yeah.
Yeah, thank you, Rida.
I'm going
Thank
to
you.
stop recording.